So we were talking about Monte Carlo, right? Which is a way of estimating the value functions when you do not have the transition models or the system dynamics, so to say, right? Okay. So first, why Monte Carlo? Monte Carlo is needed to estimate the value functions, like I stated, where you do not have the transition functions. If you have the transition functions or the transition models, you simply use dynamic programming, the one that we earlier talked in the previous lectures, right? You use dynamic programming, you get the value functions, ideal world, extract the optimal policy from the value functions, that's it, you're good to go, you have the policy, right? But in most cases, you will not have the transition model. So you need to devise out a way or a method to obtain the value functions, which would in turn help you estimate the, or rather extract the optimal policy from that. Okay. Now, in reference to our discussion earlier about the estimates and the value function and why not use the maximum value, here, what are we doing in Monte Carlo is, first we have, okay, what are returns? What are returns? Cumulative reward. What are returns? Everyone in the class, come on. Cumulative rewards, right? Cumulative discounted rewards. Correct? Okay, that's why you have the discount factor, and then you have the reward function for that step, each step, and then you sum it. Okay, if it is a continuous episode, it will be from 0 till the end of time, infinity, right? So in Monte Carlo, what you do is, what you're doing here is, you are trying to first get the returns for the total episode, okay? And returns are not estimates. Returns are definite values. Why? Because you know the reward that you're getting, right? At every step, you move from A to B, B to C, C to D, right? And you get some values here. You get, say, +1, -5, +16. Some random values, right? So your total return starting from state A would be +1, -5, +16. That would be +12. Okay? This is GT from A, your total return from A. Your total return from B would be 11. Your total return from C would be 16. Okay? These are returns, these are definite values, as in, yes, you are going to get that. Okay? You go to this here now. This transition will give you -6, this would give you +22. Okay? Now the value of A would be -6 +12, 22 would be +16. Okay? Initially your return, value of a return is +12. Here your value of return is +16, okay? Meaning that from state A, if you take certain actions and you reach the termination condition or the terminal state, you will end up now getting reward 16 rather than 12, okay? What is RL? RL is basically the way of obtaining an optimal policy. What is a policy? Series of actions, right? So ideally, what should happen is, so you know that, say this one will give you even less, this one will give you +1, -3, +6, okay? So here you will have +1, +1, -3, +6, that would be +7, 4, okay? That would ideally mean that if you are in A, do not go to any other state except C and then go to T, right? That would give you the highest what? Highest return, right? Now, This is assuming if you take a right from A, you will go to C, and if you take a left from A, you go to B. Okay. Now, this is the situation where you have a deterministic transitions. You remember deterministic and stochastic transitions, right? That is, if you take an action and you end up in an exact same state always, 100% of the time, it is a deterministic action. However, if you take an action and you do not always reach or end up in a known state S dash, but rather you go to some other S double dash, say 20% of the times you go there, 80% of the time you go to another state, despite taking the same action. Then, what are you doing? You have a stochastic action now, right? Okay. So assume this environment is stochastic. Okay. Initially, in the first step, in one iteration I am doing, I say in state A, take action right. It does. It goes to C. Then it goes to T. Okay. Now I am like, fine. The ideal policy for me here is right and right. I learned that optimal policy. I'm like, okay, fine. Now I go deploy. Okay. I'm in state A. I see what's my optimal policy. It's like take a right when you are in A. Like I take a right. But now, because the policy is stochastic, I end up in B, which is giving me far lesser value. It's just +1. I'm like, oh, what's happening? But this was the optimal policy. So how is it the optimal policy now? It is not. Right? Why? Because here what you are getting are the returns. Returns, what is the value function? You remember there was one formula of value function based on the Bellman expectation equation. So it had the expectation operator and current reward plus future estimates given state S. Right? Okay, here you had V as well. Right? In recursive. That is Bellman recursive equation. Expectation equation, you are using G. Right? Which is the return. S prime, because this is, okay, yeah, this is S, so this is, this is, what I meant here is Rs plus gamma Gs plus 1 given you're in state S. Okay, clear now? Yes, okay. This is the value function of the state S. Clear? You have the expectation operator here. Clear? What value function will do? Okay, there was another form of value function. What was that, remember? You have summation over pi, summation over probability transition model times R plus gamma V. This is the recursive equation, S prime, and this is S, capital R. Okay? So here, when computing the value function, we did account for the action that we are choosing plus the probability of that action resulting in the state that we want it to be. Right? Are we clear on this? Here, in the value function, if we had the dynamic programming method, we were taking into account the actions that you will take and the probability of that action resulting in a given state. Clear? 100% clear, right? This is the recursive equation, Bellman recursive equation. This is the Bellman expectation equation, right? In this one, are we taking into account the probability of that action? Sorry?
Discrete actions are here.
Yes, if even here we have a discrete action, even for discrete action, this is deterministic action. Deterministic. But here we don't know whether it's deterministic or stochastic because we don't know the model at all. So we don't even know whether it is deterministic or stochastic. Right? So there's no point, there's no question of then we considering whether that equation, whether that value has taken into account the stochasticity of the stochastic nature of the action, right? So in order to compensate for that, what we have to do is we have to take returns over multiple episodes, over multiple trajectories or else, and then we average out. What is value function here? It would simply be, okay, this, if you write it in one term, what is this? This is G of S. Reward at this step plus discounted future returns. This is what? Not without expectation. Simply this equation. What is this? G of s. This is the return starting from that state. So now your value function is g of s given s. Right? Expectation. Sorry. And by expectation operator, what happens is, it is the mean. By definition, if you have an expectation of a certain variable, you have to take the mean of that variable. And that is exactly what we are doing here. What are we doing? Summing all the returns for that state over all the episodes that we have and dividing it by the number of times you have been in that state. Right? That would give you the value function of that state. Hence, this thing changes and converges towards the true value when it repeats over multiple episodes. Clear? Are we clear on this? Okay? Sure? Yes, because when you take, say you have this trajectory A, B, C, T, okay? That is because you took some actions and you repeat the same actions again. Now your trajectory might be A, E, T. Because of the stochasticity of the actions, the same actions will result in this trajectory now.
When taking the average, we're trying to adjust.
Yes. So now with these two trajectories, what happens?
Take the average.
Okay, if it is 50-50, then you get this, you get the average. But then if it is not 50-50, because you don't even know what is the probability of that, the stochasticity of it, as in what's the probability of ending up in which state with that action, you have to repeat it multiple times.
So you get a probability instead.
Yes. And then you average it. Clear? Clear up until this point, everyone? Sure. Okay? Okay. Now, Monte Carlo has two methods of computing this value function, okay? One called the first visit Monte Carlo, the other every visit MC, okay? So what does this mean? Just from the name itself, first visit Monte Carlo means you consider in the computation of the value function the return from that state only when you visit that state for the first time in any given episode. In the sense, you have this trajectory now. A, B, C, A, C, T. Okay? This is a trajectory. You take some actions, you are in A, some action, B, some action, C, some action. You end up at this T is terminal, okay? You end up with this trajectory, okay? In first visit MC, while computing the value function, what you do is, say this is GT A1, okay? As in when this, at this point, what is the expected return? 1, 2, 3, 4, 5. Let's assume it is plus 16. And GT A2, okay, would be, from this point onwards, what's the expected return? Say it is plus 3, okay? In first visit MC, in first visit Monte Carlo, you discard this reading. You do not take this reading. You simply take 16 and then whatever in the next trajectory altogether, say if you get 12, 3, 4 and 5, next in the next episode, you visit A 4 times, but you still consider only 12, plus 12, plus whatever in the next episode, plus whatever in the next episode, plus whatever in the next episode, then you divide by the number of observations. Number of observations. Right? That's all you do. Clear? This is first visit Monte Carlo. The other way is every visit Monte Carlo. In every visit Monte Carlo, what do? You consider every time that state is visited in every episode. So then in Monte Carlo, the summation would be 16 plus 3 plus 12 plus 3 plus 4 plus 5 plus whatever by number of observations. Okay? When you run this iterations, episodes, enough number of times, the value that you get for the state, that is the state value estimate that you get from first visit MC and every visit MC converge to the same value, which in turn is the true value of that state. Clear? Clear, everyone? Sure? Yes. Okay. Okay. Say this is a trajectory. Say you're in a grid world, okay, where you have states named as A, B, C, D, E, F, G, H, I, whatever. A being one state, T being the terminal state. Okay, so if you go in T, the trajectory ends there. Remember, Monte Carlo was for? No, I mean, what kind of tasks? For continuous or episodic? For episodic, right? So there needs to be a terminal condition, or rather a terminal state, where when you go, everything should terminate. The episode should terminate, right? Sorry. So you are in that kind of grid world, okay? You take some action, you record that action. You're like, I take this action, I go from A to B. Then you take some action, you go from B to C. Then you take some action, you go from C to A. Then you take some action, you go from A to C. Then again you take an action, you go from C to T. C to T, episode done. Okay? Only then, okay, also one more thing that you have to very carefully note here is you are taking the value of this GT, which is the return, and return is not an expectation. Return is the actual value that you get, right? So this value you can get only when the episode terminates, right? In the sense that only when you complete the entire trajectory, you get that reward. It's basically like, say, you're doing an MCQ exam, or you're doing an exam, okay, where the professor says you're not getting any marks for the steps. You get marks only when you reach the final correct answer. So that is how it is. You do not get marks for steps here. You cannot stop in between, right? Okay, you say, no, I have this +1 -5. So I'll work with this value, this returns. No, you cannot. You have to complete the episode in order to be eligible to consider that return. Are we clear? Okay? Yes. So you take this episode, you get this episode. Okay, A, B, C, A, C, T. Okay. In first visit Monte Carlo, okay, what is Monte Carlo? What do? You're in state A, you write the return for state A till the end of trajectory. Clear? Then for B, you write the same thing, you write the return value. C, you write it again, and you repeat this multiple times, okay? But before that, what you do here is, now here A, in that case is, every state was visited only once. Now in this case, A and C are visited twice, in the sense that in the same trajectory, you go to states A and C 2 times, right? So now which visit's return will you consider while computing the value function? Because value function is what, remember? It is summation of the returns by the number of observation. So now if you visited a state twice, you will have 2 returns from that state. So which return will you consider? Yes. So again, so Monte Carlo was like, okay, let's divide into 2 parts. First visit, every visit. In first visit MC, you consider only the return that you get from the first time when you visit that state. Rest all you ignore. You're like, I don't consider that. Okay? And in every visit MC, what you do is you're like, no, this time I went to A, I got 10 points. And I go somewhere else, I come back to A again, now I got 15 points from A. So you consider both, right? Yes.
So I think we just learned the same concept of averaging, and we use dynamic programming also. We will get the same value function of the.
How will you learn the transition probability?
I have examples for A and B and C for all the states. We have all the examples.
Okay.
So we can learn the transition.
Yeah, that would simply mean model-based reinforcement learning, where you're learning the model now. That's exactly what you do in model-based reinforcement learning. Right? You take actions repeatedly, multiple times, okay, to get the data of the output, and based on that you learn the mapping from input to output, and that you call the transition probability model. So exactly that is what you're doing. Yes, if you do that, you apply dynamic programming, simple. Okay. Where were we? Okay, yes. So in every visit, what you do is you consider every time that state is visited in that episode, and you sum that up and then divide by the number of times you visited that episode in all the episodes. in all the iterations, right? So yes, you sum up the number of times you visited that state divided by the number of times you visited that state. Clear? That's averaging basically. Are we clear on this? Sure. And an interesting thing here is, no matter what approach you use, first visit or every visit MC, you will end up with the same value of your state. That is, the approximated or the estimated value function is always the same, and it converges to the true value, right? They converge to the same true value. Okay? Clear?
One is computationally more efficient and one maybe takes more time.
Slightly more, yes. Because you have more number of observations to compute now. But given, yes, this computation thing comes into play when we really had, if we had very primitive computers. But now adding 5 numbers or 50 numbers more or less is the same thing, right? Because of the advancements in silicon industry, you have very high powered computers which can do the computation really fast. Okay? Okay. Yes.
Can you just read that last line again?
This one? Okay, I'll write it again probably technically. Value function by definition is the expectation of the total estimated returns starting from any given state S. But if we know that the immediate reward we can get it when we take one action. So we break this and we write it as expectation of the return for this time step plus the discounted future return starting from the next time step given you are in state S. Right?
There was an extra GS, I got confused.
Oh, I was writing some, no, okay, this is like this is this. This is this, and G of S is defined as this way. Okay, yeah. Right. So let's, there's a numerical example here to show you the difference between a first visit MC and every visit MC, okay, which we already did. So you have the trajectory here as ABAC terminal, okay. So in first, and the rewards are, for every step it's 0, 1, 2, 3. Okay, just for the sake of simplicity, assume the rewards are 0, 1, 2, 3. Okay. So now, can you compute what is the return from A, if you return from A for the first A? What would be the value? 6, right? Value for B, sorry, return for B? 6. Yes, 6, okay. Return for the second A, what is the return for second A? 5. Return from C? 3, right? So in first visit MC, what you do is, you consider only the first value, 6, okay? 6 and 3. For every visit, you consider both 6 and 5 and 6. So when you are computing here, you see, when you're computing the value function for V of A, assume that this is the entirety of episodes you need, the value function of A would be 5.5, whereas in a first visit MC it would be 6. For the other states it remains same, right? But then this, when done multiple times or enough number of times, it would converge again, reiterating it again to, yes, it would converge to the true value, right?
Question the reward part. Is it being designing the reward, for example,
Sorry, yes.
from A to B, there is a reward, and from B to A, a different one?
Yes.
They usually, like, because they are the same states, but like the reverse action, it could be actually different.
It could be same, it could be different. There's no compulsion that it should be the same, right? Like assume B is closer to the goal. So if you go to B, you get a higher value. But if A is away and you're going from B to A, you might get a lesser reward, right? Clear? Just like value functions, it could be applied to the action value function as well. Sorry, just like state value function, it can be applied to action value function as well, Q, and the concepts remain same, okay? So based on this again, okay. Now this was what value function, you remember we had 2 steps there if in policy iteration. Even in value iteration we had 2 steps but combined into one, right? There were 2 elements basically that we are trying to do. What were the two elements? Policy, evaluation, yes. Policy improvement, right? Up until this point that we did in Monte Carlo, what did we do? We evaluated the policy, right? Because you were simply trying to get the returns, V, of that particular environment, okay? Okay. Now when you're doing this, you remember when you were doing policy improvement, you simply took the value functions that you had for a given state for every possible actions, okay? Did you at that time care about the model of the system? Did you?
If there were probability reduced,
We did
How?
consider probabilities for each action.
Sorry, again.
Consider the probabilities.
We did that when we were computing the value function. When we were doing the policy improvement, that is when we were choosing the action, towards the optimal action, did we consider the model that time? Yes, it was just dependent on the value function. So if you have the value function, from there on it is simply selection of the best action for that particular state. Just max case. And exactly that same theory applies here. So Monte Carlo policy improvement is nothing different from the standard policy improvement that you have, right? Okay. Now, a very interesting phenomena in reinforcement learning is exploration versus exploitation. Okay. What is exploration? Exploration means you know that from this position to that door, you have a straight line path, right? I walk straight, I will go out of the door, right? That I already know it, okay? But say I'm somewhere in a different place in this room, then how do I get to that door? If I have never tried going from anywhere other than this place outside the room, will I be able to figure out how do I get out of the room? I'll not be able to do it, right? Because I have not explored the environment enough. Every time I get a chance, I simply exploit it, okay? A very relatable analogy of this thing is, say you go to a restaurant, okay? A restaurant X, you go order a shawarma there, okay? You eat the shawarma, okay? A given shawarma, chicken shawarma for example. Like, it's very tasty, you eat it, you go out. Next time you come again, okay? You look at the menu, you're like, no, I'm ordering chicken shawarma again. You again eat a chicken shawarma. You do that again and again and again and again. And one fine day, your doctor tells you, you cannot eat chicken anymore, okay? But the only option available now is that restaurant. You go to that restaurant, what do you eat now? All your life, you have just eaten chicken shawarma. So what do you do then? You will have to start exploring options, right? At that time, probably it might be a little bit difficult for you because you have already eaten chicken shawarma a lot there. You haven't even tried their, say, lamb burger, right? So that is how you balance. But at the same time, if every time you go, you try a new dish, you will never really fixate on one dish in that restaurant, right? So you have to balance this exploration and exploitation. This is one of the most interesting phenomena in reinforcement learning, the balancing of exploration and exploitation. Okay, you need to know exactly when to stop exploring and actually exploit it. Okay, exploit, I didn't talk about exploitation. What is exploitation? Exploitation is basically if you know that something is good there, you keep on taking that without worrying whether the neighboring place has a better thing or not, right? Say there are two restaurants, you just go to one restaurant, take the chicken shawarma just from there, right? There's a restaurant right beside it, probably that serves a tastier shawarma, but because you never tried, you never know, right? But at the same time, say you go there and the shawarma was really not good, you simply waste your money. So while exploring, there is a chance of you not getting the best possible outcome that you want, right? So this balance between exploration and exploitation has to be very carefully maintained, okay? That's why in the future lectures you will see that a lot of RL algorithms, or rather DRL algorithms, deep reinforcement learning algorithms, include a balancing term for this, where initially you explore more, and as you go towards the convergence of the value, you reduce the exploration and you do exploitation more. That is okay, fine, I have explored it enough. Even if you go once, twice, that's still fine. I've visited every place. I know how it is. This is my favorite place. I'll go there every time. Right? That is exploitation. Yes. So now what we do is to balance this exploration and exploitation. There are several ways in different algorithms, okay, where you have a decaying factor or you incentivize exploration more. Many such things. Okay. One such method in Monte Carlo to promote exploration is called epsilon greedy method. Okay. This is probably the most easiest and most interesting solution people came up with for exploration. Okay. What they do is they simply have a term, name it as epsilon. Okay. And they're like, we have this set of actions. Okay. They're like epsilon if the, and then they simply say roll a die. Okay. If the number is less than epsilon, they take the maximum action. If the number is more than epsilon, they'll be like, okay, let's try something new. Crude sense. Okay. Mathematically it's something different, I'll explain. But this is how they do. Okay. You put a threshold, you roll a die. If the number is less than something, you're like, no, this time we're going to take the maximum value action. If the value is, if the roll of die gives you a number more than the threshold, you will simply take a different action. And you do this multiple times over multiple episodes. Clear? That's exactly what epsilon greedy is.
So it means like once in a while, try something different.
Exactly. But that once in a while, how do you decide once in a while? By that roll of die. Right? So that is nothing but epsilon greedy. Okay?
Does it decrease?
What?
I mean decrease. You mentioned about when we're close,
Yeah, no, in this one it doesn't.
so it's static.
Yes. Because the decaying factor and all those are in more advanced RL algorithms where you have deep learning. Even in DQN is also is neural network based, so it is DRL. So yes, so take a random action with probability epsilon and take the max action with the probability of 1 minus epsilon. That's it. That is epsilon greedy. Clear? This is how people came up for the balancing of exploration and exploitation in Monte Carlo. Right? Very simple but very interesting. Is it not? Yes.
How do we define this epsilon?
It's arbitrary. That's the interesting thing. You take any number between 0 and 1, you're like, this is my epsilon now, and you let it be for the entire training. You're like, okay, epsilon, this thing. 1 minus epsilon, this thing. That's it.
So it's hyperparameter like this.
It's a hyperparameter. Almost everything in reinforcement learning, even reward function for design for that matter, is a hyperparameter. Because for a same given task, if I tell you people to design a reward function, I will get at least out of say 20 people here, I'll at least get 7-8 different reward functions, completely different reward functions. Yes.
What's the word decay?
Which K?
I heard the word decay. Is here in
DK.
decay? Yeah.
No, it's not here. It's in advanced algorithms. Okay. So, what are the advantages of model of pros and cons of Monte Carlo? Basically, a summary. Okay, Monte Carlo, you do not need a model of the system. Good, right? And then it can learn from simulated or real-world interactions. Obviously, like any other algorithm, R algorithm, it works well only with episodic environments, or even if it is a continuous environment, you have to have your discount factor such that it makes the reward after a certain point 0. Implying that the reward after certain number of steps would simply be irrelevant. Okay, you remember the horizon that we calculated using the discount factor? So you have to have a finite horizon, even if it is a continuous task. Only then can Monte Carlo be applied. Why?
At the end of each episode, you need to see the values of each state.
Returns of each state. Okay. Any other answers?
We have got an end for each episode to Monte Carlo works.
Sorry?
Because Monte Carlo has to be to have episodes.
Uh-huh.
So in continuous system we have to have episode on this infinite.
Why? Why do we want episodes?
Because it's averaging over the episodes, averaging the combinatorial rewards or the value function. So
Okay.
episodes to average.
Okay. Any other answers? I just recently saw a research actually which says that the average attention span of today's people or today's audience is 8 minutes. And after that, you lose the audience basically. So I want you to be more involved in the teaching so that you actually learn from the class, right? So come on, more answers. Yes.
Is it biased somewhat?
What?
As like this word said, is averaging all the observations and so on could have like give all things equal importance, and maybe some values are more important, like to look at from some way other.
Okay.
Like the things high variance, we're biasing, or maybe, I mean, not giving full information, we're equally calculating every part.
Okay, okay. So yes, there are two words that come into play here, bias and variance, okay? Bias is basically how far away you are from the true value, okay? Remember what I said about Monte Carlo returns? What were you doing? You were actually taking that action and actually getting that reward. Everything here is actual. It is not estimates here. There are no estimates involved in the returns, right? So there is no chance of bias in the sense, okay, still you will say that, okay, no, but why? You are still averaging it, so there should be some bias, right? What was the initial assumption that I said? Or the initial requirement for Monte Carlo is that you repeat the episodes enough number of times so that the bias is eliminated, right? You remember the coin toss, the funny coin toss that we did, which happened to be 3-3, but then what would you do in real time? Like say you're tossing the coin, say 500 times. You will not get exactly 250, but theoretically it should be 250, right? So you do this over many, many times, which would in theory tend to infinity. If you do that, you would get half heads, half tails. Thus the empirical proof of having 50-50 probability when you toss a coin. So exactly here, theoretically you have infinite episodes. When you do infinite iterations or infinite episodes, your values, the estimated or the computed values will converge to the true values, right? And next term that you talked about is variance, okay? What is variance? Variance is the change in this estimated value function over every episode, okay? Now this has high variance, okay? Why? Because yes, we are taking random trajectories, so the variance will, in this episode, like here in this case, it's from plus 12, it goes down to plus 4 or something, the value changes significantly, right? So this is variance. Yes, Monte Carlo has high variance but low bias, okay? Clear?
What defines enough episodes again?
What defines enough episodes? Okay. We'll then stick back to the initial dynamic programming concept I told you. It isn't a dynamic programming computing. When this change is below a certain threshold, and the threshold can be a very, very, very small number. Okay?
Like a residual.
Sorry?
Like a residual.
Like a residual. It is when it is very small. Okay? And back to that question of why we need episodic environments or environments or systems where the returns after a certain horizon is irrelevant. Why? Because you remember what we are doing here? We are computing the actual rewards we are getting till termination. That is why you can only work with it for episodic environments. You're considering actual returns, right, for the entire trajectory till termination. That is why you need episodic environments or episodic tasks. Okay. Yes. However, yes. So some of you pointed out that which is more efficient, first visit or every visit Monte Carlo. That basically are very small numbers. So that you can add as many as you want, right? It is not computationally very demanding. However, say you have a very complicated task. Okay. Say dynamic obstacle avoidance in 3D. Okay. That would be a very challenging task. So can you think of the number of paths it would do, the number of episodes it would have to do? It would have to do a lot of episodes, right? And every episode, the termination time would be very, 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 very long, right? At times it might simply go to a path, stuck somewhere for a very long time, then come back, hit the environment, then go somewhere, and say hitting the environment is not your terminal condition. Then again, it will fall, it will again get up, again finally it will reach the goal, right? So you see that the trajectory itself is very long. The entire episode. And remember, you have to wait for the entire episode to compute the value function, right? So therefore, this is one of the major drawbacks of Monte Carlo. That is, the trajectory can get prohibitively long, very, very long, right? Which would in turn then increase the computational demands, because this trajectory that you're doing, you're either doing it in simulation or real world. And these are computationally demanding processes, right? Clear?
So
Yes.
it will not work with the continuous tasks, or it will not work well.
It will, no. It will not work with continuous tasks that do not have a definite horizon. Why? Why?
Because we cannot compute
We cannot compute. The episode never ends, so therefore you can never compute the total return. If you cannot compute the total return for that state, you cannot use it for the averaging, right?
because it's written there, cannot work well. So I thought that can work, but not well.
Doesn't work well with infinite horizon. This is the key term here, infinite horizon. That's why it's highlighted. It doesn't, oh, it doesn't work well. No, no, no. It doesn't work at all. Okay, it doesn't work at all. Yes, it doesn't work at all with problems which have infinite horizon. Okay? Yes.
What are some algorithms that use this? You mentioned DPG.
Sorry?
I mean, Monte Carlo method has algorithms, right?
Right?
What are some of them? Because we mentioned in the beginning while talking the process,
Yes.
DPG and
Yes.
TD3 and
Yes.
are some of them Monte
No,
Carlo
no.
method?
All of that I talked about are TD learning.
Or-
Yes. We'll be learning about it later. TD, probably in the next lecture. Okay. So yes, just summary. Dynamic programming requires a model. Monte Carlo doesn't require a model. Dynamic programming doesn't need full episodes because you're using estimates. You can keep on doing the estimates. Monte Carlo does require the termination of the episodes. What is bootstrapping? Okay, bootstrapping is another term that you will hear in the next class in more detail. Bootstrapping is estimating basically. Okay, value function by its mathematical definition is an estimation, right? Which is what you use when you are computing the value functions using dynamic programming, right? So therefore, there is some kind of bootstrapping in the sense there is some kind of estimation. However, with Monte Carlo, you are using the actual return, so there is no estimating here. Hence, no bootstrapping. Clear?
Why full episode? Like you said no for DP, full episodes.
Yes.
Why?
Okay. Because you do not have to wait for the episode to terminate. What do? You simply take one step from state S to S dash, and then what do? You are like rewarded this state plus the discounted estimate of the next state. Discounted value estimate of the next state. You're not considering the returns here. And value function by definition is an expectation. Or if you know the model simply, you can calculate it till whatever horizon you want. Or even if it is continuous task, because the value of every state, you do not have to wait till the termination of the episode to compute that value.
You just said till the end of the horizon, right?
In this case, the horizon can be infinite.
In DP.
In DP. Because you're simply estimating the values, you're not actually doing the actions to get these kind of rewards for every step and then computing the returns. You are rather calculating the value function, which by definition is an expectation of the returns. Right? So yes. So you're simply expecting the returns from a given state, given you follow a certain policy.
The bootstrap, I would have thought it's the other way around.
Sorry?
Bootstrapping is
Estimating, yes.
So, like with Monte Carlo, isn't it like an estimate?
No, it is not. Because what are you using in Monte Carlo? Okay, the value function that you're getting by Monte Carlo is through this formula, V equal to 1 by n times, sigma g, returns, right? These returns, are they real or are they estimates?
Oh, yeah, because it's episodic.
Episodic, yes.
So in case of DP,
Dynamic programming, okay.
estimates. Can you
Okay.
give us an example of where we could do do estimates?
For every example that we did, what did we do? When we moved from A to B, and there was some other task, other trajectory that had to be followed to reach the terminal condition, we did not care about what we were doing here. We simply have V of A equals to reward of A to B plus the discounted value of being in B. So this VB again, say from VB you take B to some state S, which is then gamma times V of that state. And this value function, how are we calculating it? Through this expectation function, which is an estimate. Expectation is estimation.
Yeah, but like we used to do this. We used to back up from the goal states, right?
Yes, that is because the examples that we did, we had a finite horizon or an episodic task.
So when you're talking estimates, you're talking about continuous.
Yes, yes. If you have a continuous which doesn't have a end, so to say, then you cannot compute the returns for every state. You will simply have to use the estimate at that point. That's why you have the bootstrapping, right? Clear? And we could do that in dynamic programming, because how did we compute the value function? We could simply compute by this formula. We didn't have to actually do it, right? Because we knew the model here, we knew these things, we could simply mathematically calculate the value function and then plug it in, right? Right? Clear? Sure. Okay. Okay, variance and bias, like I said, in Monte Carlo the variance is high because you're considering every episode where the returns might change significantly. However, in dynamic programming it is smaller, the variance is smaller. Why? Because you're using estimates and you start with some initial guess. The first step might be a little bit high variance, but after that the changes will be gradual and eventually they decay and die down till you converge to the true value.